Next, we're going to talk about the velocity problem. So remember, we are interested in the instantaneous velocity. So the velocity of an object right at one instant in time. And the idea here is that we find the average velocity on some time interval that has a size delta t, or maybe we'll call it h in this case. And then we consider that the size of that time interval is going to go to 0. So delta t will go to 0 or h will go to 0. If we say that s of t is the position of our object and we have a time interval that starts at a and then has a length of delta t, so instead of using delta t, maybe we'll use h, then the instantaneous velocity at time a would be the limit as the size of the interval h goes to 0, s of a plus h minus s of a plus h subtract a. So what you notice again is that the formula we are left with looks an awful lot like the derivative formula from before. And in fact it is. This is just the derivative of the function s at time equals a. This would be s prime of a. This would be the instantaneous velocity at time a. Just turns out to be the derivative of position at time equals a. So this object called the derivative comes back again. So if we let the position of some object be capital H of t is 58t squared, let's find the instantaneous velocity at some time equals a. So the instantaneous velocity would be the derivative of this position function at a, and according to what we wrote above, we'd have to go h of a plus little h subtract h of a, all divided by little h. And remember, this represents the average velocity of the function on the time interval, and then we're making the size of the time interval go smaller. Usually where students get some headache is with this function notation. So the t is just what we call a dummy variable. It's a placeholder. We don't even need to have a t. Whatever you want to put here, you just copy and paste there. We are going to need to do this twice in this formula. H of a, you just replace the t with an a, so you'll just get a 58a squared. But the big H of little a plus h usually gives students a lot of trouble. So it's a plus h, the whole thing goes in the bracket and then gets squared. And so that means it's going to be a plus h times itself. You're going to get a 58a squared plus 2ah plus h squared. You have to make sure you're using the rules of algebra correctly. You'll get a 58a squared, 116ah plus 58h squared. What happens next is you take all of those things and you plug them into the formula, the derivative formula. So you'll get 58a squared plus 116ah plus 58h squared. That's from this first quantity. And then you'll subtract a 58a squared divided by h. Now it becomes a limit problem. There's a little bit of cancellation that can happen here. We're right back to the story and the message that I tried to give you before. When you're faced with a new strange limit, the first thing you should do is sneak a peek. Because it's 0 over 0, there will be no limit laws. You have to do a little bit of algebra first to clean it up. The only algebra you'll have to do is to factor out a common factor of h, and you'll find that that's the thing that's causing the 0 over 0. Once you do that, everything that's left is easy. There is no more 0 in the bottom. The limit laws will apply, so go ahead and apply them. This whole thing is a constant. A is a constant. 116 bunches of a constant is still a constant. There's no need to separate anything there. The h is what we call the limit variable. Constants can come out of any expressions with that. And all that's left is a 116a. So that means the velocity at time a is 116a. This gives you a formula, a function for the velocity. If you want to know the velocity at time 1, all you do is plug in 1 into this formula. You'll get 116. If you want to know the velocity at time 2, you just plug in 2 into the formula. You'll get 232. And that's essentially how you end up using limit laws and the derivative formula to help you calculate things. Now, there's one last thing that I want to do and talk about this interpretation. The velocity is the derivative of position. But we also know from the formula here that velocity is what we call the instantaneous rate of change of the position with respect to time at time A. If you look at this formula, we've got position changing upstairs and time changing downstairs. The limit is what makes it instantaneous. The rate of change of position is up here, and with respect to time ends up being down there. So in general, if I've got a derivative f prime of a, we are going to say that it's the instantaneous rate of change of my function f of x with respect to x at some value x equals a. And I don't really care what the meaning of those variables is. This is what makes a derivative powerful and what makes it be able to be used in one situation to another. The instantaneous part comes from a limit. Which function is changing? It's the thing upstairs. And what is it changing with respect to? Whatever the variable is downstairs. And this allows us to generalize the derivative as an important tool. It measures how things change in all sorts of circumstances.